My name is Megan Van Veen. I'm a geotechnical engineer here at BGC, based in our Ottawa office, but presently coming to you from Vancouver. And I'm really excited to introduce you to two of my colleagues, Alex Graham and Vicky Hsiao. Alex is a GIS developer and Vicky's a senior GIS analyst. And today they're going to talk to you about recent advancements and new tools that we've developed to support LiDAR change detection analysis, using examples from a recent project in the Pacific Northwest. When I first joined BGC about 7 years ago, LiDAR change detection was something that was very much seen as kind of a specialist skill. Some people called it black magic. And the way that we did it was really manually and highly time consuming, which limited how we could apply it. But with some of the new tools we've developed over the past 3 years, thanks to a really awesome group of folks here and a lot of collaboration between different groups, we've really been able to take this from something that was area limited to something we can apply really efficiently to many different projects, ranging from site specific to thousands of square kilometers of areas or linear corridors, without sacrificing accuracy and quality. So with that, I'll pass it over to Alex and Vicky and let them show you what they've been working on.
Thanks, Megan. Awesome introduction. Yeah, so on the screen here, I've got a direct shot from our Cambio software platform of a pretty infamous landslide in Oso, Oregon. And that'll be part of the example that I'll pass over to Vicky in the second half of this presentation. So I'll go through the first 2 bullet points here. I'll summarize LCD, as we call it at BGC, and go into a little bit of technical detail about how we do that, which includes alignment and then the actual change computation. And then I'll leave it up to Vicky for the case study and some of the learnings from those results. So this figure here with 3 charts is aimed at really describing the evolution of the last roughly 4 years of change detection in Cambio in our software platform. And so we've got the number of clients accumulating over time at the top. In the middle, we've got the number of change detection data sets that we've produced. And then at the bottom, the total area that those cover. And so I've added a black line there at roughly 150,000 square kilometers. That's about 0.1% of Earth's landmass, or equivalent to about the area of Washington State. So this really describes, what Megan was saying was, prior to the timeline here, we did a lot of things manually. They were in reports, static figures. And as we've grown and scaled our process, we've really picked up the volume that we can do this kind of work. So this slide here just summarizes the workflow currently of how we produce LiDAR change detection. We have a standard request process where we gather information about the project and who's involved, things like that. And then we've spent a lot of time in the last couple of years developing open source tools, particularly in Python and R, that are geared towards cleaning, organizing, and preparing point cloud data ready for change detection. The next 2 bullet points are really talking about how the change is computed, which one key piece of that is aligning data sets. And then towards the bottom, we have a custom piece of software that Alex Ferrier at our company built. We call it ALS Change, and it leverages graphics processing units. And that really allows for the speed at which we can compute change. And then lastly, we have our Cambio platform, which really serves to map, provide analytical tools, and serves as an inventory of change detection data sets. So here's kind of the overview of the technical details and how change is computed between 2 LiDAR data sets. We first have to divide the area of interest into what we call sections. This varies depending on whether it's like a linear infrastructure type of asset or perhaps a mine site. We generally use a regular grid for mine sites and divide corridors into sections roughly 2-3 kilometers in length. And then for each section, we have to align the point clouds. And I'll get into that a little bit more in the next couple of slides. And then for each point in the newer point cloud data set, we actually compute a local surface, and the change is then computed perpendicular or normal to that surface. So here's an example, a cross-sectional view of 2 example point clouds, time 1 and time 2. And this would be an example of how they come at face value. They have a bit of georeferencing error. You can see on the left and the right side of the point cloud that the terrain is quite similar, and there is a little bit of shift involved. And so what the iterative closest point algorithm is intending to do is match those similar places and align the two data sets together so we get something like this before we compute the change. And so that ICP algorithm, it does rely on similar features in both point clouds. It assumes that and matches them together. Here's an example of results on the left and right. The left being change computed without the alignment process, and then on the right with the alignment process. And as you can see, it removes a lot of the noise, makes the results much cleaner, easier for interpretation, and more precise. When you think about computing change between LiDAR, there's kind of two main methods. The more basic one I'm going to describe here, which we would call a difference of raster DEMs. And so this would involve creating a DEM from each point cloud, and those blue and green squares would be the pixels of each DEM, and then you just simply subtract them. This is fast and is easy to do for perhaps areas that have lots of change and you're not really concerned with really small differences in terrain, but it does not capture those really subtle differences. And so what we do for the majority of our change detection data sets is a point-to-point difference, where, like I said, we compute a plane or a surface, a local surface for each point in the time 2 point cloud, and then we get the change distance from or along that cylinder there in the figure, and that yields a much more precise result than the DEM differencing. So yeah, that pretty much summarizes our change detection process. And now I'll hand it off to Vicky to describe the case study in the Pacific Northwest.
Yeah, thank you, Alex. So now you have learned the fundamental of LiDAR change detection, and here I would like to share the change detection results at kind of multi scales. So we're starting from the small scale, which is usually it involves a few square kilometers of the data. And what you see here on this image is the gray images you can see is a hill shade and derived from the point cloud. And on the top of the hill shade is the change detection. So the change detection you can see from the color scale. So for the blue scale is showing the negative change, and the warm red scale is showing the positive change. So in these results, you can see the change detection highlighted in the lens side. You can see a negative change and followed by the positive change. So this is a case study in the West Coast at California. This is the most common one in a scale, which is the smallest case studies but frequent in BGC. And the next one we call it medium scale, which is involve hundreds of square kilometers of area. And in this case study is in District of North Vancouver. So this is covers 9 years of the surface change in the city setting. So in this case, what we want to say is we are not sacrificing the data quantity from the quality. So in the small scale to the medium scale and to the last one, which is a regional scale that I want to focus a bit more in this one. So this is a case study in the northwest of Washington State, and from here you can see this is the border between the Canada and the U.S. And this is the one of the largest project we have processed for the change detection in BGC. In this case, we can see the 11 years of surface change, and just a little of close up when we're looking at Washington State. We always look at also lens side here, which is you see on the screen here. So a little detail of this project here in the regional scale of LiDAR change detection. So what is different from all the rest of change detection? This change detection project we did in BGC is because it is a beast. It is heavy. So the data, the point cloud we process it is over terabytes of data, and the area of the project is over just within the 1,000 square kilometers of the region. So in terms of the spatial extent and also multiple chain detections, we have processed. This is one of the single project we have processed the most of LiDAR chain detection in within the BGC with all the different vendors and different precursors as well. And this project is funded by Washington Department of Natural Resource. And shout out to Mel Leto, Mike Van Veen, and Luke Werner, and Alex Graham. So, and our PM, Julia Fraser, all they contributed to this project. And how is the project turn out? How is our results? And here is some of the examples I want to share with you. So in this image here, you can also see, now you're familiar with our color scale, negative change and positive change. We're looking at clear over landslide over here. This is along the South Fork, Nooksack River. And this is another beautiful screenshot of also landslide showing up to 10 meters of change at, this is between 2013 to 2017 of surface change here. And this one is really beautiful. You can see the landslide. You can see the spatial extent was captured from the LiDAR change results over here. And this image is kind of giving us a little bit of landscape setting. So we are looking at more flat of topography, looking at the surface change within the same project here. So within this regional scale of LiDAR chain detection, what do we learn and what we see the value in the data? So LiDAR chain detection, we know it can uncover the unknown landslides, and it is one of the most effective technology to monitor surface change. It can also provide early warning, and it is scalable. We can look at data in a very small scale, but we can also look at a huge region. And what's the pain we learned from this project? As we know, there are so many different sources and vendors from this project. And so first step is sorting the metadata, sorting the data based on the metadata to organize data and convert the different units.
Vicky, sorry to interrupt. I think somehow you muted yourself there.
Okay, can you hear me now?
Yeah.
Okay, should I start from this slide again?
Perfect.
Okay, so in a regional scale LiDAR chain detection project, particularly in the WNF project, what we learned is the LiDAR chain detection can uncover unknown landslides, and LiDAR chain detection is also one of the most cost-effective technology to monitor surface change, and it can apply early warning monitoring, and it is scalable. We can monitor a small site, we can monitor a huge region as well. And what's the pain we learned from this regional LiDAR chain detection project? As the data is provided from all the different sources. So first we have to organize the metadata, organized data based on the metadata. And also the LiDAR comes with different units, different projection, and different projections. So we have to convert everything to the same units and projections before we can process data. So we're looking at apples to apples. And the last one, data transferring, something surprising me is data transferring still take a few days as we are downloading the data directly from the portal online. And if we are working directly with actually LiDAR vendor, we often actually request the vendor to actually put the data into hard disk and transfer the data to us to the Vancouver office. Sometimes we learn the old school way is still the best way. And the LiDAR chain detection, what's the limitation? So the LiDAR chain detection quality is actually heavily relies on the quality of the source of data. So if the data resolution is poor in the original point cloud, or is misclassified, or there's a snow cover on the data, then all this we will see actually this impact in the chain detection results output. And fortunately, is all this limitation we can actually trace back to see in the source of the point cloud. And what's the going forward? What do we see in the LiDAR chain detection world? I would say the more the merrier. So particularly in a small critical site setting, we're going to see the more frequency of the data collection. We're probably going to see the daily, weekly, or monthly of data. And with the evolution of technology, for the airborne LiDAR, from the UAV, from the photogrammetry, we're going to see the data collection being collected more commonly and also more widely. So the data will be available for a site all the way probably to a country level. And what is the turnaround processing time for our LiDAR chain detection? So typically, if we are looking at a size scale, we can almost offer a near real-time information, because once the data is in Vancouver, in our office, then we're able to process data within a few hours, and then the results will be available online. Can be able to provide that to the end user. And in a large scale of a project, in terms of thousands of square kilometers of an area and terabytes of the data, in this one, as BGC, we have a patented algorithm to process data very effectively and efficiently. So in the large scale of project setting, we are able to do the pre-check of data, processing data, and the post-check data within a time frame between 4 to 6 weeks of timeline for large scale LiDAR chain detection. And now thinking about, we have all the big data from a sort of LiDAR chain detection with big area with different temporal time frame, and how we digest or extract the information from this mass data is probably the next area we will want to explore more. And this is how we'll conclude our LiDAR chain detection presentation to share with you here. And thank you. Open for questions if you have any.
Yeah, thanks, Vicky and Alex. That was really awesome. We do have a few minutes for questions. Terry, I got to imagine it's pretty late where you are. I don't know if you wanted to turn your mic on and ask the question, or we can read it from the chat. Okay, so we'll read it. Or Alex, I don't know if you can see it. The question is, very interesting presentation application. Do you need ALS point cloud data, or can you work with gridded DEMs? And then how do you subdivide very large regional data sets into smaller segments for the ICP alignment? So just for reference, Terry did his PhD on this exact topic. So a very well informed question.
All right, thanks, Terry. Yeah, I can take that one. So the chat was loading for me. Yeah, so like I said, if we want to achieve that alignment, we do need the point clouds. We can always, do change on gridded DEMs, though there are some caveats to how precise the results are going to be. In terms of dividing the data sets into chunks, for things like mine sites, things that are smaller, we do just use a regular grid. But for linear assets, we have been manually chunking up the corridors, the right-of-ways, to avoid boundaries on critical slopes, for example. But we are looking into ways to automate the generation of those sections.
Okay, thanks, Alex. There's a couple questions in the Q&A chat as well. John, I don't know if you wanted to ask your question. We can read it out loud. With respect to geohazard inspections, how do we see the application of LiDAR change detection to site inspection or site inspection frequency?
Vicky, do you want to take that one?
Yeah. Oh, sorry. Can you repeat the question again?
Yeah, I can help too if you want.
Yeah.
How do we see the application of LiDAR change detection to for pipeline inspections, site inspection or inspection frequency?
Yeah, Matt, you want to take it?
Yeah, I can help out with this one. So John, a really good question. And as data is getting better and better, like some of the new data we're looking at has limits of detections of 5 or 6, 7 centimeters, which over a 4 or 5 year period, we're looking at really small movements over time. And I think what we're getting to the place of being able to do is certainly flagging sites for a faster inspection frequency because of recent movement that we're seeing. And then certainly on the other side of delaying inspection is an area that we're working on. And when we start to pile together the LCD and the IMU data, I think we're making good progress on being able to move in that direction, but that obviously takes a little bit more care. There's one more question. And Vicky, this is, I think, a perfect one for you, but how can you relate the work that was shown on INSAR before to the LiDAR change detection, and how do these how do these two products complement each other?
Yeah, I think this is relates on the basically how much we can detect. So for the InStar specializing in very slow movement, which is from the millimeters to probably up to a few 10 centimeters of the change. But for the LiDAR train detection, I think we want to see something actually between the two acquisition, we can monitor something up to over 0.2 meters of change. So that's kind of the main differences of the two technology. They complement each other. Yeah.
Okay, I think that's awesome. Thank you very much, Vicky and Alex. And we'll now hand it over to Matt, another Matt, to introduce